Do you have any questions? Okay. So, uh, we'll continue today to talk about 4.5. So, mean time spent at a transient state. Okay. So, basically, the idea is this, right? Give me a moment. So, we know from the previous study of, classification of states that if you have a, Markov chain with transition matrix P, then the Markov chain, right, can be basically classified into different classes, right? Communication class, class 1, class 2, right, etc., right? And out of these classes, right, each of these classes can be either transient, right, or recurrent. Okay. And the point is basically, eventually, right, the Markov chain will end up in one of the recurrent classes, right? And they'll leave the transient classes, right? So eventually, right, XT will be in some recurrent class. So we have then right, we basically, in terms of 4.4, we discussed how within that recurrent class, right, the Markov chain will be in different states, etc., right? Stationary distribution. So, or, in other words, basically, 4.4 study the Markov chain when it has been inside, right, one of the recurrent classes, for example. What we will talk about here, right? Or, so okay. So on the other hand, if you have more than, one class, right? More than one class. So when the Markov chain is not irreducible, right? So this is not irreducible. Then there are two questions you can ask. Basically, the probability that XT will be absorbed in, let's say, one recurrent class, let's say recurrent class A, versus, let's say, recurrent class B. Okay. So basically, I mean, of course, right? So, okay, maybe I should say this is starting, right? at some transient state. The reason, of course, is that if you are in a recurrent class, you will stay in that recurrent class and you will not escape. So the question is, right, if you are in a transient class, right, you will be absorbed in some recurrent class. But which one, right? Which one? So what's the probability in some recurrent class versus another one? All right, that's the first question you can ask. And second, you can ask is that, well, you know you will be eventually absorbed, but expectation, let's say, of time until absorption, given some transient state, okay? So the second one is really a topic of 4.5. This one, let's say, is just a question that's naturally there, right? That I put down as a question that we can take a look at. But probably there's not, I mean, we can say something about this, but not kind of like a nice result, a nice equation to write down. But both of these, okay, naturally occurs as kind of questions. Basically, right, the question is about moving from a transient state to recurrent state, right? Sorry, moving from a transient class into recurrent class, right? So let's say the setup we have is that we have at least one transient, one recurrent class. Okay. Because when you think about it, if you have all recurrent classes, then there's no question. Because if you are in a recurrent class, just stay there, right? There's nothing about making the transition from one recurrent class to another. Sorry, from one transient class to a recurrent class, right? Yeah, there's no transient, there's no movement, right, from one recurrent class to another. On the other hand, if it's all transient, for example, then the changes keep moving, right? Like one-dimensional random walk, right? One-dimensional random walk without going anywhere exactly. So in between, you have something like a transient class and a recurrent class where you will end up in a recurrent class. But let's say which one, if you have more than one recurrent class, and then how long, right? So let's say the classical example that something like this would happen, right? Not, this question can be raised for many, let's say, Markov chain. But the classical example that would happen here is the so-called gambler's ruin problem. Okay. And so the context, so basically, right, the gambler's ruin says that the gambler has an initial fortune, right? Let's say it's K, where it's between, let's say, two ends, right? 0 or end. So basically, this gambler wants to win N dollars, right? Let's say to buy a house, whatever you want. And so the gambler, right, this is the goal, right, the target. Okay. Or, you can also think that basically if this guy has to gamble against someone else. So this person has initial fortune K, so the opponent initial fortune is N minus K, right? And so each of them will play, a game, a series of game, right? Where from our gambler's point of view, he will win with probability P and lose with probability 1 minus P, right? Okay. And so basically, right, I guess from the opponent's point of view, they will win with probability 1 minus p and lose probability p, whatever. But both of them will play, right, until the first one hit 0 fortune, right? Or they will play until the first one among themselves go bankrupt, right? Whichever. And so that's why, right? When our gambler reaches n, that's the same as opponent reaches 0, right? In terms of their fortune. Or if our gamblers, right, goes bankrupt, then they have nothing, right, to gamble with. Okay. And so you see, basically, this is really just a fancy way to describe a finite, right, dimensional random walk, where you go to the right with probability p and goes to the left with probability 1 minus p, where, right, both of 0 and n can be viewed as absorption, right? Because once you go there, you do not analyze the Markov chain any further, okay? And so, two questions you can ask, right? What's the probability that, let's say this, right? So we know that eventually the random walk will end up at either n or 0. So what's the probability that, let's say, our gamblers, not being ruined? Or it's up to you, right? Because of course, one is the complement of the other. But let's say what's the probability our gambler, right, made it, starting with fortune k, right? So that's exactly this question, right? What's the probability that we get absorbed at state n rather than at state 0, right? So that's actually a very, let's say, popular question, right, that people asked about a gambler's ruin problem. Then, of course, the second question is, this is kind of independent of, not independent, this is separate from the first one, but if you let tau, right, be the first time that the game stops, right? Either way, right? Notice you cannot say that it's the first time. Well, I guess you could, but if you just do this, right, then this tau has a positive chance of being infinity, right? With infinity being it's never reached because the Markov chain ends up at being 0. So you have to define like this so that, right, this tau is finite for, the probability is finite 1, right? So anyway, so this is the what you call it, the expectation of the absorption time, right? Expectation of the absorption time to absorption, right? Or expectation of the length of the game, right? Expectation of the length of the game. And so, right, both of these questions are really the questions we're asking here, right? I mean, but we're going to answer this in a little bit more general details. But I mean, we can also just focus on this, doesn't matter. All right, any question? So, actually, right, let me backtrack. We will just, for this question, we're just going to focus on gambler's ruin. Because as you can see, the question depends on the structure, right, of the transition matrix and which recurrent class we're referring to, right? If the Markov chain has more than 2 recurrent classes, then we need to specify what they are. So for that question, right, for this question, let's just focus on the gambler's ruin problem, right? While the expectation of the absorption time, we will, sorry, I have to say this, right? This is condition, right? This is tau k, which, you know, this here, right? So notice that unlike the long-term proportion, right, of time spent at a state, here, these quantities depend on where you are initially, because these are transient states, right? Where you are initially matters. But if you go back to 4.4, the analysis there is all for recurrent states. So therefore, it doesn't really matter where you start. The answer will be the same, right? Independent of where you start here. The answer depends on where you start because we're looking at transient states, okay? And so, yeah, let's start with this, right? Let's see here. No, so let me just say, first of all, the answer to both of the questions really is not surprising. Both questions use first step analysis. That's all there is, right? You just let the Markov chain make one move and see what happens, okay? Condition on the first step. All right, so quiz one, right, for the gambler's ruin problem, right, let's say pi sub k, right, here, okay, be the probability that the Markov chain end up at n starting at k, right? Write down a recurrence equation that pi k has to satisfy. Okay, so look at one-step conditioning and see what happens. What must pi k satisfy if the chain if the gambler, right, play one game, what happens to the probability of getting absorbed or winning a game, right, rather than losing a game? All right, so what's the answer? So you see, right, when you make a move, so the probability, right, that you win a game clearly will be the probability you win again if you gain one fortune times p, right, one extra unit, and then plus 1 minus p times this, right, where this is valid for correct. And then what else? What else is, you know that pi 0 equals to 0, because if you are at 0, right, the chance that you will win the game will be 0. And then pi sub n will be 1, right? Because if you're there, right? And so you see, this is you can say it's recurrence equation, but it also, right, if you view this as k plus 1, k minus 1, I mean, I'm just showing you, right? If you really, I forgot it goes backward or downward, forward, but let's just say this, right? Pi k plus 1 is, let's say 1 over p pi k minus p pi k minus 1, right? Like that. Then this, right, you see, gives you a two-step, right? So how you move from k minus 1k to k plus 1. Or of course, right, you can do, pi k plus 2 is 1 over p pi k plus 1 minus 1 over 3 over p pi k, right? It doesn't matter. As long as, you kind of readjust the k so that the range is valid, right? The range for this equation is valid. But the point I want to show you is that here you see that you move two steps forward, right? With like basically the probability, right? I mean, this is really not time, right? This is fortune. But if you view this as time, then two steps forward depends on the previous, two steps. So this is called the second order finite difference equation. Or is there a word finite, or it's just difference equation, second order difference equation? This is in contrast to what? This is in contrast to the, not contrast, but in comparison to what? This is analogous to second order differential equation, or second order ODE, ordinary differential equation, right? Because, the derivative is with respect to k, right? So basically, this is a difference equation, second order, because you move two steps up, right? The equation makes a connection between two times step forward, right? With boundary conditions. So it's not an initial condition. Let's say versus, right? This is what you want to kind of think of in terms of reference with boundary conditions, okay? And, difference equations will be studied, or you will study about that in a course in, let's say, discrete math. I'm not sure you study in combinatorics, but you study in discrete math, for example. The technique for solving it, is sort of similar in some way to solving differential equation, right? You make a guess for the equation and then you solve it, right? But all in all, like, I mean, you could, all right, basically play around with the structure, right? And try to see what the solution looks like. But what I want to mention here is that there's really a systematic approach to solving this equation as well. Or there's some kind of special trick, doesn't matter, right? That's, once you write this equation down, it's really a system of equations, right? There are like k equations total. Then you just solve for all the pi's using some techniques. Any question? Now, because this is really a technique for solving equation, there's really not much we need to say about this, and that's why, right? Basically, for the first question, as far as I know, there's no real topic that was set down as like, okay, here's an equation for this kind of question, because the system you set up, I suppose, depends on how transition matrix is structured and what kind of absorbing classes you're looking at, right? For the Gamblers-Rhin problem, this is the system, which is a second order difference equation, right, with boundary conditions. Okay, so let's write down the solution. And let's see if you can guess this, right? When p goes to 1/2, which is the symmetric, right, random walk, what do you think the solution is? So pi k is a half, right? Pi k plus 1 plus a half pi k minus 1. Pi 0 equal to 0. Pi n equals to 1. So what do you think pi k would be in this case? And by the way, right, so actually what we use here is sort of like uniqueness of solution, which is basically a topic, right, you prove separately somewhere, but you prove that this difference equation can only have one solution. And by solution, we mean the solution to the system, right? The vector pi k. Once you say that, once you prove that, then it may sound unsatisfactory. But suppose you have a answer you can guess somewhere, and you plug in, it works. Then that's the solution. Period. Right? And of course, I would fully admit that it's not super satisfactory, meaning I don't show you how you solve the system from beginning to end. But it's really not the point of this class. So we're just going to write down the answer. But if you want to study that like systematically, you can look at that topic. But what should the solution be here? Well, because it's symmetric, you can see, right? It should look like it depends only on the initial fortune, right? Meaning that if you have, the more you have, the easier, right? You will get win, right? So looks like it's k over n. Let's check. Is that true? K over n is that true? That's 1/2 k plus 1 over n plus 1/2 k minus 1 over n. Seems true, right? And does it satisfy the initial condition? Absolutely. Therefore, it's the solution, right? So I'm just showing you, right? I mean, there are other ways you can solve for this pretty easily if you are given the time, right? Especially because it's 2 and 2. So on the other hand, if p is not equal to 1/2, can you guess what pi k would be? So pi k in this case will be 1 minus q over p raised to k divided by 1 minus q over p raised to the n. Okay. Well, of course, q here is the notation for 1 minus p, right? Once again, you can take a look into, the textbook or the so that if you want to look at how they solve for this, right, in the textbook, it will be in example 4.5.1. Okay. But like I said, it's really just a clever way to arrange this equation, right? And then solve for them. But let's check if this is true, right? Again, because if the solution is unique, then it's satisfied, right? So is it true that this 1 minus q over p raised to k is it equal to p, right, times k plus 1 and then this is Q, right? 1 minus P. K minus 1. So you see, right here, the numerator, the denominator doesn't really matter, right? It's the same denominator. So basically, it's just really the sum, right, over K of all these quantities is equal to that, right? Wait, hold on. Am I saying it right? Does a sum of all the pi k's have to be equal to 1? No. Sorry, it's not true. The sum of the pi k's doesn't have to be 1, right? Because it's on different conditioning. It's conditioned on different steps. So anyway, right, these are just some other numbers to make things work, right? Makes into a probability, if you will. But let's see here. So this is 1 minus Q over P raised to K, right? And so if you multiply across by P, this is P. What's the easiest way to do it here, right? So okay, here P plus Q, right, is equal to 1. That's good. And then you got one of them will be Q to a K plus 1 over P to a K, right? Because you multiply across by P. And then here, when you multiply across by Q, you got Q to K over P to K minus 1, right? All right, so what do we get here? The common denominator here clearly is P to K, right? When you multiply by P here. So you got 1 minus, right? Q to K plus 1 minus P Q to K over P to K, right? So you factor out Q to K here. Sorry, it's a plus, right? If you factor out Q to K here, you got 1. So it's really right. So the equation is satisfied, right? Well, is it true that pi n equals to 1? Yes. Is it true that pi 0 is equal to 0? Yes, right? So actually, maybe that's really for the boundary condition, right? Otherwise, you see in between, and also will satisfy that it's between 0 and 1, right? Otherwise, it's true. Any question? All right, so there you go, right? So that's gambler's ruin. And in general, right, like I said, it's really just some kind of system of equations for the probability, right, of getting absorbed into one class versus another class. But not much more we can say about, right, what to do with the system. Besides that, it's some kind of difference equation you solve. Now, so let's tackle the second question. The second question, which is what? The absorption time, right? So, okay, I phrase it here in terms of absorption time, right? Time to absorption. But if you think of this carefully, right? It's like this. Let's look at the gambler's ruin, right? You start initially, you have K, right? K units of money. Then at K unit of money, you could what? Spend time, right? Meaning along your movement to state 0 and state n, you could spend time at state K itself, state K plus 1, state K minus 1, state K minus 2, etc., right? Each of them will be spent at finitely many steps, right? So in other words, let's say the time to absorption here, tau K, right, really will be the sum of times that the number of times you visit different states, okay? Starting at K, different transition states, transient states. So in other words, let's say if you denote, let's say Sij, okay? is the number of times xt goes to j condition on x0 goes to I, where right here, notice that if, let's say, both ij are recurrent, then this will be infinite, right? Because if they're both in the same recurrent class, then they're both infinite. Then Sij equals infinite because you will keep going back to j, right? Infinite many times. So here, right, what we're looking at is when they're both transient states, then you only visit right j finitely many times starting at I if both ij are transient. Also, right, tau k here, you see in terms of Sij will be the sum, right, of Sk, let's say j over all j transient. Do you understand? Right, because the time until absorption, right, will be the total number of times that you spend at different transient states, starting at wherever the transient state that you started with. So basically, even though I call it absorption time, like this, absorption time like this, it really is a sum of the number of visits to different transient states, as starting from some other transient state. In other words, this object right here, right, Sij will be what we will write down the equation for. And once you write this down, then this object right here, which is the expectation of time until absorption, can be solved for. All right, any question? Okay. So yeah, right. So let's write it down again. So if you have ij transient, right, you denote S sub ij is the number of times xt goes to j condition x0 goes to I, right? Well, you note, okay, that this question doesn't really, or this question has trivial answer, or this question is connected back to, right, the following. Suppose that if you look at SII, right, and what is it? It's exactly, I think, what we call is n sub I, right? It's the number of times the Markov chain visits state. So this is here, this is t greater than or equal to 0. So you also count, right, the first time, the initial time, right? The number of times you visit state I starting at I. Remember this? Where, right? What is it? It's really a geometric random variable, remember? With what kind of success probability? With success probability 1 minus Fi, right? What's Fi? Fi is the probability that you will return to I starting at I. This is sum t, right? Right, remember way back when we looked at this, right? So basically what I'm trying to say is for Sij here, this is a generalization of Sii. The reason is because, right, you do know then expectation of Sii is 1 over 1 minus Fi. We know this from the previous analysis. What we want to find out is expectation of Sij in general. That's the project here. I mean, that's the goal here. Okay. Any question about this? Okay. So what do we have? Oh, by the way, right? So what I want to say is, you see, this is why it doesn't make sense for either one of them to be recurrent, because the answer will be either 0 or infinite, right? Depends on how you look at it. If this is a recurrent state, then the number of times you revisit a recurrent state will be infinite, right? If this is recurrent and let's say this is transient, then you will not really go to a transient state. You will keep going back to a recurrence, right? Because there's a chance you will not revisit the recurrent state. So we will still do one-step conditioning. Right, meaning that if you are at I and you make one step movement, how would the Sij look? So let's see if you can write this down. Write down the equation that Sij satisfies by one-step conditioning. All right, so what's the equation for Sij? So as you can see here, right, it's a sort of like a interesting thing, but the way we set things up, right, which also works for the geometric random variable, is that you do count the first time you are at state I starting at time 0 as 1, right? If you do look at Sii. Therefore, right, if you are, let's say this, right? So basically, if you are state I, right, then roughly speaking, you're looking at something like this, right? Pij S, sorry, Pik Skj, right? Something like that. So the number of times, right, you visit state J starting at I will be the probability that you visit some state K, and then the number of times you visit state J, right? From that state K, correct? Because that would be how you visit, right? But so here, notice that you could, let me see how we can phrase this. You could move from I to J directly, right? Which count as 1. And then you can move from J to J. Sorry, give you one moment here. So there's a consideration when I equals to J and when I is not equal to J, right? When I is equal to J, well, okay, so let me just let's write down something like this first. So roughly speaking, this is the idea, right? Sum of all transient states, like that, okay? But you have to kind of take into consideration whether I equals to J or not, because of the way we count the number of visits, right? Starting at I, right? Because at time equal to 0, then you count as 1 visit. So let's see. If, let's say SII, right? If you are at I, then you automatically have 1 visit, right? And then you can move from I to some other state, and then count, sorry, you can move from I to some other state, and then count the number of visits, right? Or, sorry, you know what? I think I wrote down the wrong notation here. Let me backtrack. SII itself, right here, is already an expectation. Sorry. So SII here is already an expectation. So SII is expectation of the number of times, like that, okay? So, like that, okay? So here, yeah. If you are from I to I, you already have 1 visit, then either you, so then you will have 1 visit, then you can move to another state, K not equal to I, right? Or if you are I is not equal to J, then you just move to a transient state. Because, right, you cannot have a 0, you cannot have a number of visits being 0, right? You cannot have a 1 visit first because I is not equal to J. So just move to another state and count the number of states you visit from there. So again, right, this 1 or 0 comes from the fact that we define the number of times, right, you visit counting from time t equal to 0 rather than t equals to 1. Does this make sense? Any question? So, but notice that these two together, right, actually gives you a matrix equation. So if you collect together, right, the S matrix, okay, which is a matrix over all transient states. Then this equation reads as the matrix S is equal to, so this is only one, right, if I is equal to I, and 0 if I is not equal to J. Therefore, it's really an identity matrix, right? And then this is PIK times SKJ is really P times S, but this P here, right, is P only over the transient states. So this is a P, the portion of P over the transient states. Does that make sense? And so therefore, right, this will read as S times I minus P sub T is equal to I, or S is equal to I minus P sub T inverse. Okay, any question? So this looks highly abstract, right? But let's look at one reality check to see that this really works as it's intended to do. So the reality check is as followed. Let's suppose that we want to go back to this question. I want to verify that SII is 1 minus 1 minus F, 1 over 1 minus Fi, right? So how do we do this? Suppose we only have one transient state. Okay. And you want to find the number of visits, right? So expectation of the number of visits to state I, starting with I. Can we do that? Okay. So let's analyze, right, to answer this question. Let's analyze Sij further. So Sij, right, is expectation of the number of visits, right, of xt to state j starting at I, okay? So which will be let me see here. So in regard to, right, so if you remember, if you let Fij is the probability that xt is ever at state j, let's say was some t when equal to 1, right? You will ever go to state j starting at I. Then you have this following equation that Sij will be, right? So delta ij plus f ij times sjj. Okay, where delta ij will be 1 if I equals to j and 0 otherwise. So this is an equation, so this is Sij. This is an equation, right, connecting Sij with Sjj, right? So that's exactly the expectation number of visits to state I starting at I. So really is number of, you know, we can look at this, right? But the connection is via, right, this number. And let's see how this works, right? So the number of visits to Si from the expected number of visits, right, to state J starting at I will be 1, because, right, if I is equal to I, then it's 1. If otherwise it's 0, times, right, so plus the number of visits from state J to state J, right, and then the probability that you ever goes to state J starting at state I. Does that make sense? So, right, let me explain. So this, right, again, right, this comes from, right, so if you ever, right, go to J, then it's going to be the number of visits starting at J, right, going to J from J to J. But if you don't make it to J, right, because this Fij, right, could be, is less than 1, right, because the number of visits from state J starting at I, Fi, both Ij being transient, is less than 1. So if you do not make it, then it's really just if you don't make it to J, so if you do not make it to J, then the number of visits to state J, oh, okay, so here, right, if you do not make it to state J, right, so the point is this, if you do not make it to state J, then basically, maybe let me write it down and then I'll explain. So this is supposed to be, right, this delta ij here is a little bit, it's supposed to be like this. So it's supposed to be like this, and then it will simplify to that, right? So let me explain. So if you ever go to J, right? If you ever go to J, then it's just a number of visits, right, from J to J. The delta ij here is because of this, right? It's really just to take care of the case when I equals to R, I equals to J. So when I equals to J, right, then it reads as SII is 1 plus, right, SII times FII plus, right, 1 minus FII. Okay. And this is because of the following, right? The number of visits from I starting at I will be 1, right? If you return back to I plus number of visits because you already have 1, or you never return. If you never return, then you actually have 1 visit, right? Which is the initial visits. The initial visit when t equal to 0, right? So it's like this, right? Either you have only 1 visit and you never comes back, or if you come back, right, then this is actually the geometric, right? 1 minus fi equation, condition the first return. But if I is not equal to j, okay, then this reads as Sij is equal to, this is 0, right? And you got Sjj times Fij, and that's it, right? This is equal to 0. And so if I is not equal to j, then either the number of visits to j starting at I depends on whether you get to j or not, times, right, the number of visits to j starting at j, right? Because if you never make it to j, then you never visit I to j, right? So to visit from I to j, you have to make the transition from I to j first, and then, right, start a visit from j to j. And if you combine these two together, right, it's this equation. And this equation, if you factor out, right, the delta ij, you get this, right? And then Fij times Sjj being that. Okay. So, sorry, it was a bit confusing because you have to separate out, right, the two cases here, because the state I visiting itself is slightly different from the state I visiting some other state. But all in all, right, once you have this equation, then the point is that the probability, right, that you ever visit a state starting, say, JS starting at state I can be solved like this. Okay. So the point is that the probability that you ever visit a state, transient state starting at another transient state, can be solved using the matrix, right? The expectation matrix that we looked at above. Okay. And the reality check that I mentioned, if you have a transient state I, then what's the expectation number of visits to state I starting at I? The answer here, of course, supposed to be 1 over 1 minus Fi, right? 1 minus over 1 minus Fii. That's the expectation. Well, does that agree with this answer? Well, let's see, right? Fii, right, is it equal to, right, Sii, right, delta ij is 1, right, over Sii, which is what? 1 minus 1 over Sii. Well, the answer is yes, right? Because if you turn around, right, you got 1 over Sii is 1 minus Fii. in other words, right, FII is, sorry, SII 1/1 minus FII, which is what we want to check here. Is that okay? So by looking at, right, the probability that you ever visit a state J starting at I and write down the equation, right, for that in terms of SII, you can relate the probability of you ever visiting with the expectation of number of visits. And these two, right, agree with the case of one transient state, as we looked at before. Any question on this? And so, right, so to recap, basically, for the expectation of times that you visit a transient state, starting a transient state, right, the mean time spent in a transient state is captured by this equation. And once you solve for this, then, for example, right, okay, let's take a look at the gambler's ruin problem. For the gambler's ruin problem, you have state 0, state 1, etc., right, up to state n. Both of these states are recurrent. In between, right, you have the transient states. So your matrix P, right, will be like this: 1, 0, 0, right? And then you got 1 minus P, 0 P, 1 minus P, 0 P, right, etc. Until you have 1, 0, 0, 0. All right. So this is the matrix P. The P sub T portion, right, the portion that corresponds to transient states. So P here is n plus 1 by n plus 1, because there are n plus 1 states, right? State 0 to state n, the n plus 1 states. P sub T portion, of course, will be the portions over here, will be one minus P, 0 P, right? 0, 1 minus P, 0 P, etc. Right? And then ends up with 1 minus P, 0 P at the end, right? And this will be n minus 1 by n minus 1, right? Because this is only for states 1, 2, etc. up to state n minus 1. And if you, I don't know, right, take I minus P sub T inverse, I suspect, right? So if you do I minus P sub T, then that's 1, right? 1 minus that is P. And this is 0, right? And this is going to be minus P, right? And 0, P, 0 minus P, right? And you got 0, sorry. Hold on. 1, 1, 2, 2. Did I write this right? Hold on. Sorry. Then the what's the last thing here, right? One, 1, 2, 2. position here is one, one, two, two, 1 minus P. What's the last row here? When you have P here, 0, 1 minus P like that, right? For the next to last row, which if you cut it back, it will look like this. The only thing I have question for, this is the end position. This is a 1, 1 position, right? But the structure is 1 minus P, 1 minus P. Why is it that the last one ends up at P rather than 1 minus P? Sorry, give me a moment here. So did I do it right or did I miss it? So 0, 0 here, 1, and then 1 minus P, 0 P, that's correct, right? And then 1 minus P, 0 P, that's correct. Either way, right? Sorry, somehow I kind of messed up the last row here for the I minus PT portion here, because somehow it seems like the first two positions, right, or all this position, the position is 1 by 1, 1, 2, 2, 3, 3. But the last row, it doesn't seem like the position is n by n here for 1 minus P, right? It seems like P here, so something does not line up quite correctly. But either way, let's move on. The point is, if you look at this matrix, right, and then you do I minus PT inverse, which is this matrix inverse, then that will be the S, right, which is the number of visits you go from, let's say, state 1 to state 1, state 1 to state 2, state 1 to state 3, etc. If you take once you take the inverse. And so for our question, which is tau k, is the expectation of the number of times, right? Expectation of, so tau k, right, is the number of times xt, spends at the transient state before absorb, right? Starting at x0 equals to k. Then expectation of tau k here, for example, will be just a sum, right? Once you look at this matrix S, then you just look at the row k, right? The row k here. And you sum over skj, sum over oj. So basically, it's just a sum of the row k, right? Of this matrix, the inverse of it. That will be expectation of tau k, because it will be the number of times you spend at all the transient states starting at k, right? So that would be the length of the game, right, for the gambler's ruin problem starting at k. Okay, any question? All right, so beyond this, I don't have much to say about Markov chain, anymore, right? There are other topics, for example, time reversible Markov chain, hidden Markov chain, and things like that. That's you can read about that on your own. For the last like half an hour or so, what I want to do here is I want to kind of tell you about two other, right, special random processes that we don't have time to look at in this course, but sort of like some general kind of introduction about those stochastic processes. So when we look at, so two, right, other examples, right? Two other important, let's say, examples of stochastic processes. So the first one, so remember, right, when we look at Markov chain, I mentioned that you look at how the time variable behaves and the space variable behave. And you can have discrete time or continuous time. You can have discrete space or continuous space. So if both time and space are discrete, then you have Markov chain. Discrete time and continuous space, I was saying that it probably is some kind of sampling of, discrete of the continuous Markov chain, of a continuous time process at a discrete time points. So we don't have really a name for this thing. But if you have continuous time, discrete space, then a good example for that would be Poisson process or point process. And if you have continuous time, continuous space, a good example for that would be Brownian motion. And so I want to talk about these two. Okay. Now, believe it or not, both Poisson process and Brownian motion are quite similar in some way. I mean, not totally, right? But they're both continuous time process. So if you have a continuous time process, meaning xt, and let's say t between 0 and infinity, continuous, then the challenge here, right, is how to describe the distribution of xt, or the joint distribution. It's like this, right? If you think about it, with Markov chain, you have probability xn plus 1 is somewhere, or xt plus 1 equals to somewhere given xt, right? So I'm switching back to n here because you want to distinguish that from continuous time variable. What Markov chain has is that you have a time point and a time point before that, right? So n is immediately before n plus 1. All right. And so basically you describe the probability here at time n, you are state I, and here at time n plus 1, you are state j. In between, there's nothing, right? Because there's no time in between. But you have a continuous time Markov chain. Your first challenge is that you do not have a time immediately before another time, right? If you have a continuous time, right? Sorry, did I say Markov chain? I say a continuous time. You can have continuous time Markov chain too. But let's say, So actually right here, continuous time discrete space, you can probably is something called continuous time Markov chain, right? But if you have continuous time in general, then there's no immediately time point before time t. All right. In other words, if you have t here, right, and you want to look at how you move to t, there's not really like, say, a time s here. And then from s you move to t, like from I you move to j at time n to n plus 1. Between s and t, right, there are uncountably many time points. And you have to be able to describe the joint distribution of all the value of the process in between these time points. Okay? So there's not really a discrete structure where you move from one time to another, but time moves continuously, and you need to describe how this works. And that actually is the challenge, right? Once you move away from discrete time. So discrete time, right, is sort of Markov chain structure. Once you move away from discrete time, then the nature of continuous time, right, is that you don't have any immediate time before. So you have to somehow show, right, the joint distribution over a continuous range of time. And it depends on what you work with. But for example, if you have a continuous time Markov chain, then there's something called a forward-backward Chapman-Kolmogorov equation you write down. But with the Poisson process and the Brownian motion, okay, these two are special because they rely on the following structure. Both Poisson process and Brownian motion, right? They rely on the structure that they have independent and identically distributed increments. And in a surprising way, this is enough to characterize the joint distribution of a stochastic process. How so? So first of all, right, let's try to understand what increment is. An increment is for a time s less than t is xt minus xs. Basically, it's the change, right, of the process value from time s to time t. That's an increment. All right. So if you were to draw a picture, basically, right, here's s, here's t. Basically, here's the value at time s. And let's say here's a value at time t. Then you look at how it has moved from s to t. Okay. And it's a random variable, right? Because from s to t, you could either move down or you can move up or whatever, right? And you move a random quantity. But when you say it's independent, what does that mean? If it's independent, what that means is, let's say from time s, you move to time r. And from time r, you move to time t, right? So there are two different movements. From s, you move to r, and from r, you move to t. Then you say that the movement from r to t and the movement from s to r, they are independent of each other. That's independent increment. What about identically distributed? Identically distributed means that over each time interval, right? Let's say from R to T, this has a distribution that is sort of like only depend on how time has elapsed. For example, this is a normal random variable with mean 0 and variance T minus R. So in other words, right, the change, how the process move from time R to time T, in general, it will be a normal distribution. So if you are at R here, right, in general, you don't move anything. But the variance of your movement depends on how long time has passed from T to R, right? And you see, if you say this, then automatically from time S to times R is the same thing. XS minus XR will be a normal with mean 0 and variance R minus S. And it's identical in the sense that the distribution is the same, right? The family is the same, but not the, variance, right? It depends on time. And you see, right? What these two requirements is enough to give you everything. Now we know everything. Why? Because, for example, right, let's say you want to know the joint between, let's say, x sub t1, x sub t2, x sub t3, x sub t4, right? Then what would that be? Well, you see, x sub t2, right, is really x sub t1 plus x sub t2 minus x sub t1, right? X sub t3 is really x sub t1 plus x sub t2 minus x sub t1 plus x sub t3 minus x sub t2, and so on, right? So it's a weird way to write like this. But if you want to know the joint between two 4 time point value, basically it's the same as the joint of the initial distribution, plus all of these are independent of each other. So it's like you make independent movement, right? From the initial distribution, you make the first independent movement to xt2, and then you make the second independent movement to xt3, so on and so forth. And so the joint here can be, let's say, easily written down using the independent and identical structure of the increments, okay? So by the way, I forgot to tell you that if you have this is Brownian motion. So Brownian motion is a continuous time, continuous space process whose increment is a normal random variable. Why, by the way, right? Why would this be continuous space? It's continuous space because a normal random variable, right, is a continuous random variable in terms of the values it can take. If you have exactly the same structure, but if xt minus xs is a Poisson random variable, all right, with rate lambda, then that's a Poisson process. Okay, and so you see, because the Poisson random variable take on discrete values, therefore the increments here, right, the change between t to s, let's say, can only take on discrete values. Therefore, the process itself can only take on discrete values. That's why a Poisson process is continuous time, discrete space, random process. Okay. Now, last but not least, right? Remember that if you add in sum of independent normals, it's a normal random variable. And if you do sum of independent Poissons, then you get a Poisson random variable. And that's why, right? These two are really the only two, Brine motion and Poisson process, right? Are the only two random variables that have, closure in terms of the sum. And that's why, right? When you look at the joint distribution here, it's basically the joint distribution of independent normals or independent Poissons. So it's relatively easy, right, to analyze the behavior of Brine motion and Poisson process. Notice, right, with these guys, we do not look at transition probabilities. We don't look at transition matrix, something like that. The reason is not because we don't do so. They're hidden inside the distribution of the increment, right? So instead of doing something like this, what you look at is you look at probability that xn plus 1 minus xn is equal to j minus I. Condition on xn equals to I. So that's how at least, right, one way that continuous time process is given by this structure. And so by doing this, it kind of avoids, right, the idea that to move to the next time point, I need to know where I was in the immediate point before that. I don't need to discuss that, right? I don't need to look at how you move from one point to another between any two time points. And that's one way to describe a continuous time process. Okay, any question? All right. So let's tell you, for example, right, what are some applications or some use for this Poisson process and Brine motion, for example. So there are a lot of use for these processes, but one possible use for Brine motion right? One possible use for this is in terms of, the area that I study, which is math finance. They can be used to model a, let's say an asset price, right? So asset pricing model. Namely, like something like a stock, okay, or even a bond. But how would that work, right? So basically, if you analyze, let's say, a stock model or a stock price, right? So stock price, as you think of it as moving in continuous time, let's call this S of t. What property, right, should it satisfy? The first thing is that the stock price itself, right, does not have independent increment. in other words, right, if you look at the change of the stock price, let's say from today to yesterday, let's say, and you look at the stock price movement from yesterday to the day before, these two should be related somehow. Okay. I think in a way, right? They say that like the higher, right, the stock price, it tends to imply higher increments. Okay, which is something like this. If you have stock trading at $1,000, then maybe a regular movement will be, let's say, $10 a day or more, $50. But if you have, right, so if you have $1,000, then a movement a day can be either in the range of window of $50 on average movement. But if you have a $1 stock, then you should not have a $50 movement, right? You should have something like, I don't know, 10 cents or 15 cents or whatever movement, okay? So what this points to is that there's some kind of scale factor in terms of the increments, right? The increments here depends on the value of the stock price, right? The higher the stock price, the higher the movement, right? The increment, let's say within a small time window. So that's why, right? These two are connected via ST, because if ST is high, both of these might be high. But if ST is low, both of these might be low. So the observation will point to that the increment itself for, let's say, a stock model should not be independent. However, if you look at the scaled version of this, so this is called the return, then we can expect that these are independent. Sorry, right, divided by S of R. You can expect that these are IID, independent, identically distributed. Okay. So what does this represent? This represents the change, right, of the stock price from T to U divided by, right, the stock price at time T. So this is the percentage return, right? This is the percentage return on the period T to U, okay? And this is the percentage return on a period from R to T, for example. And so what we're saying is that the percentage return on different periods are independent. And well, so the word identically distributed here, right, should be read in the spirit of, it's sort of like it's identical, but it's time dependent, meaning that the longer the time, right, the higher the variance, which makes sense because, you know, the longer the time, the more the higher the variance in terms of what return you can get. All right. And so what we end up modeling is that we say that, well, let's say that this will be a normal random variable, because let's say the return is symmetric, right, over some sort of rate of return, let's call that rate mu, times the range of time, which is U minus T, and then some variance rate times U minus T. Okay. And so, and then, right, you also specify that the return over non-overlapping periods are independent. And so if you look at this and you look at a family of normal random variables over continuous time, right? Because time is continuous here, right? Time is continuous here, right? Then what you connect back to what you think about Brownian motion model, then you will conclude then, right, that this right here, what we're saying is that this should be, okay, first of all, something like mu times u minus t, because it's just really the return, but plus sigma times something like w, so let's call it b sub u minus b sub t, where b here is a Brownian motion. All right. And so what happens, right? Let's check that this is true. The Brownian motion, the increment of the Brownian motion will be a normal random variable with mean 0 and variance u minus t. Okay. So if you multiply this by sigma, then that's going to be normal with mean 0 and sigma squared u minus t. And if you add this with mu times u minus t, then you see that's normal with mean mu u minus t, variance sigma squared u minus t, which is exactly this. Okay. And so in the asset modeling, this is called the rate of return, right? This is called the drift. This is how, on average, your stock moves. And this is called the noise term. Because this is how, basically, it gives the random, right, movement to your stock. And sigma right here is called the volatility term. Because the higher the sigma, the more volatile, right, the more the variance here will be, and the more it will kind of, the higher the variance of your return, right? And so you have analyzed, right, the return of a stock into different components like this. And the role, right, of the Brownian motion is that it gives, it's not itself the noise, but the change of the Brownian motion, okay, gives you the noise for the return of the stock. And what people do is time, because with discrete time, right, the time are one gap apart. Okay. And so basically, then if you push u to t, then this becomes dst, right? So, sorry, maybe I should write down. So in general, su minus st, you call delta, let's say st, which is a change in stock price. But if you push u move to t, then the change here becomes dst. D stands for the differential of the stock price. And so if you move u to change u to t like this reads as dst is mu, right? And you bring the st here on up, you got mu st dt plus sigma st, and then this becomes the differential of the Brine motion, dBt. All right. And this right here is called a stochastic differential equation. And the Brine motion, once again, right? So this is a whole different area of study. I just want to point out that this Brine motion, which is a part of the study of, let's say, continuous time stochastic process, right? Is a continuous time, continuous space stochastic process. It is the driver, if you will, right? It's the driver of a component that would define a stochastic differential equation. Without this, right, what you have is the regular ordinary differential equation. Again, that one that we saw at the beginning of today's lecture, right? Without this component, then you have a ordinary differential equation. But with the Brownian motion part, and you look at its increment, it will provide the random part to the movement of whatever you're looking at here, which is a stock price. And that, right, gives rise to a random equation called, right, a stochastic differential equation. Well, let me tell you, right, for the last 10 minutes or so, the story doesn't have to stop here, right? So this is Brownian motion. Where does Poisson process fits in? Well, the Poisson process can, it might be surprising or not, fit in quite conveniently into this model. How so? Because if you look at SU minus ST over ST, right? So that's the percentage return. If you look at this as the rate of return times the length of time, plus, right, some noise term. So you can think of this as regular trading movement, meaning that the activity of trading changes the stock price or the percentage return in a smooth way. But once in a while, you might have some shock, right? And the shock in the market might be determined like this. So let's say there's some value here, right? I don't know, let's throw in let's call it gamma, okay? So here's the thing, right? So here, this is a Brownian motion, and this is the Poisson process. So N is a Poisson process, okay? And this will model the shock or a jump, okay? The reason is the following. Remember, right? A Poisson process behaves exactly like a Brownian motion, except that the increment here is a Poisson random variable. And we look at, right, in continuous time, we look at this in the context that basically the time are quite close to each other. But if the time is quite close to each other, then Nu minus Nt, right, remember, is a Poisson random variable. Basically, it can either be 1 or 0 with some sort of probability, right? We won't get to that, but with some probability approximately, and 0 with some other probability, right? So the reason is, if you have a Poisson random variable with a very small rate, then basically, remember, right, it's like a binomial with the probability being the success probability being very small. So, but in terms of the model, right, basically you're looking at right? We're just looking at the Poisson process part. Here's 0, right? And here's like a very small window of time. Then either, right, a lot of times the process just stays at 0. But if it stays at 0, that means you have no movement here. And the movement is regular stock model, which is regular trading. But once in a while, you will have a jump, meaning you will jump to 1, right? You will jump to 1. In that sense, right, if gamma is, let's say, negative, then you have a downward jump because this is always 1, right? It jumps up. But if gamma is negative, then you have a negative return, negative contribution to return, but which is a shock though, because it doesn't move continuously, right? It moves with a discrete value. So that would be a negative jump to the model. But of course, if gamma is positive, right, then there will be a positive jump to the return, right? And so the Poisson process, right, can be also incorporated into this model. But because the value is discrete, it doesn't move continuously, but it moves with a jump. Sometimes it moves, but sometimes it doesn't. Well, it doesn't move, right? It basically, the term is not there. It represents just regular movement of whatever stochastic process you're looking at. But when it moves, right, when it has a sudden jump, right, exactly at the point right here, where it jumps, right, you see that you are at 0 movement and then suddenly you jump to the 1, right? That's a shock, right? So if you look at the value of the stock itself, it'll look like this, right? It moves continuously and suddenly here, it will have a jump. Let's say jump up. And suddenly here, let's say it has a jump down. So these points right here is when the Poisson process jump. All right. And in between is when the Poisson process stays at constant value. So Poisson process, right, can dovetail very nicely into a model like this to model the shock part, right, of a, let's say, an asset. And by the way, right, basically, I forgot to mention, the Poisson process also has the property that it has independent and identically distributed increments, same as Brownian motion. Therefore, when you use it to model the return of an asset, the independent increment part will still be preserved with the Poisson process. In other words, right, when you say that the returns on different time window are independent of each other, that's not changed when you add the Poisson process component into it. Okay. So again, right, these things are, like I mentioned in the announcement, not on the final exam. So I just want to kind of give you some ideas of, some other stochastic processes that we do not cover, let's say, in any kind of details, right, in this class. But you will see this used in, let's say, a quant finance course, for example. And the treatment there is completely different from the techniques we use in this course, right? The foundational groundwork is still probability. All right. So in that sense, right, chapter 1, 2, 3 are still very useful, right, for the study of these materials. Chapter 4 material is specifically for Markov chain kind of analysis. Okay. But so I guess the point I want to conclude here with the course is this, that when it comes to stochastic process, each type of process has a unique technique that can be used to study that class, right? You study Brownian motion in a different way than you study Poisson process. Well, they're kind of similar, but it's still slightly different. And then, right, they're completely different from, let's say, Markov chain or continuous time Markov process, right? The only, let's say, unifying framework, as far as I can see, is probability, right? The probabilistic techniques will be the same across all the stochastic processes. But once you specialize, right, in one particular class, then they have their own techniques, like, transition matrix, like absorbing states, right? Like eigenvalue, eigenvector, that kind of thing. So, well, we only have time to focus on one particular class, I guess, which is Markov chain. But if you see, right, these processes in your future studies, right, hopefully, like the ones the techniques you picked up from chapter 1 to 3, right, in this course will be helpful. But in that sense, chapter 4 is only peculiar, right, for any kind of Markov chain application. Beyond that, I don't quite see that how it can be relevant. All right. Anyway, so let's stop here, right? Wednesday is final exam. It's 3 hours. It will be very similar in terms of taste to the midterms, meaning that the problems will be taken, right, from the homework or lectures, mostly homework, right? If you kind of can go through the homework problems and understand the techniques used there, should be very similar types of questions asked on the exam. There definitely will be questions asked on the materials covered after the midterm too, right? Which is the homework of week 7, right? Which is the stationary distribution, limiting probabilities, that kind of thing. I will try to make the questions equally distributed among the topics, right? But there's no guaranteed, in the sense that if a topic doesn't have a lot of questions to be asked for, like let's say chapter 1 and 2, right? Then probably there would not be as many questions asked as in, let's say, chapter 3 and 4, because there are more questions, right, that can be asked in those chapters. But no single topic will be heavily favored, in the sense that you will not see all Markov chain questions, right, in the final exam. You should see sort of like hopefully, right, a spread out, right, of questions across the topics, but don't expect like something like a exactly uniform distribution, right, across all topics. The sort of like the interesting topics might have more questions than let's say the easy topics at the beginning. Okay. So if you have any questions right from now until the exam, send me an email or pop into office hours tomorrow. If not, thank you for attending the course, and hopefully I'll see you around, right, at some point. Okay. All right. Take care.
Professor?
Yeah.
Can I ask a quick question right now?
Sure.
So I was curious, what's the difference between like all different like terms like limiting probabilities, stationary probabilities, long-term proportions, and the long-run proportions? Are those different?
Yeah. So that, yes, I did explain that before, right, in the previous lecture. So in some way, they are the same numbers, right? They're all pi I. They're all the same numbers. However, they are different concepts. So long-term proportion will be the sum, right, of the number of times you go to that state and average out. Okay. Limiting distribution or limiting probabilities is the limit as t goes to infinity of probability xt equals to I. And stationary distribution is the distribution where if you start at that point, you stay there. And so you see, right, these are quite different things, right? One is sample across the times that you traverse the Markov chain. One is you look at the probability, but you keep pushing the time to infinity. And one is you're looking for a probability that if you start with that distribution, you always stay with the same distribution. And it's exactly the theorem 1 and theorem 2 that we talk about. So namely the ergodic theorem that say that they're the same for an irreducible positive recurrent, which is these two, and aperiodic, which would connect these two together. This will connect these two together, and this, aperiodic will connect these two together. So all three are the same, right? So they're the same in numerical values, but in terms of concept, they're different, if that makes sense. And so in this sense, right, you will have examples of Markov chain where they're not the same, right? What's an example of that? The example is the one where you flip back and forth, right, between the states. This one is periodic, right? This one is periodic, so it's not aperiodic. So for example, right, I mentioned before that it has a stationary distribution, which is a half and a half. Because if you start at half and a half, you multiply with this, you stay at half and a half. It has a long-term proportion, which is also a half and a half. Because it satisfies theorem 1, actually. It is irreducible and positively recurrent. So this is also a long-term proportion. However, if you look at the probability that you are at a state, let's say state 0, right? This is t dependent. Let's say it will be, right? Let's say if you start at time 0, then it will be 1 if t is even, and 0 if t is odd. Because you cannot return to state 0 if you take an odd number of steps, right? It's from 0 to go to state 1. But if you have a 0-1 sequence, it won't converge, right? The limit does not exist. Do you understand? So there are examples of chain. And also, right, for example, if you bother to look at a non-irreducible Markov chain, meaning a Markov chain with more than one recurrent class, let's say something like this. Then you'll see that you have at least two stationary distributions. Why? Because you can have a stationary distribution for this class, or you can have a stationary distribution for this class, or you can have a combination of the two. What we mean here is that there's more than one eigenvector, right, for this transition matrix, right? So basically, if you violate these conditions, so the reason is if you do the problems, right, in the homework, these almost always are given, at least in homework 7. That's why you might think that they trivially are always the same. But, Markov chain doesn't have to always follow those conditions. So that's why you could really distinguish them, right? But they're sort of like a headache sometimes to split, because these are really more like the exception more than the norm, meaning that a lot of models we look at really follow this anyway, right? So you might lump them together without danger when you look at those problems. But if you really want to distinguish a concept, then they really discuss different phenomena. Does that make sense?
Yeah. Yeah, it was mainly because throughout homework 7, it's like,
Right.
like the
Homework 7 can give you the illusion that
yeah, that's why I
doesn't
was
matter
like,
which one. Yeah, and so homework 7, as I explained last time, it mainly focus on how to solve this equation, because that's basically all we do, right? But if you move away from that a little bit, then you can have exceptions, right? That will make you feel a little bit, let's say how to say it, like a little bit annoyed to explain,
Mhm.
because somehow they still tend to follow this rule. It's still more or less this, but the language is not quite correct. Does that make sense? So if we want to stay precisely, then you need these conditions to make sure they're equal.
Okay, yeah. I just want to make sure that, like,
Yeah,
well, they have different names, so obviously there must be different things. But then it's like
correct.
throughout
So,
the
but
homework, we end
homework
up solving
seven,
it the
right?
same way each time.
Homework seven sort of like gives you the context where they're all the same. But
Yeah.
if you, yeah. Mhm. We're good.
Hmm.
Okay. Cool. All right. See you then.
All right. Thank you.